Have you ever really thought about what makes a modern car tire work so well? You'd think it's simple, right? Just a circle of rubber. But hidden inside, there's some incredibly complex science going on. Today, we're going to peel back the layers on nanocomposites, these super advanced materials that make everything from high-performance tires to cutting-edge medical devices possible. All right, so let's jump right in with the central puzzle that has kept tire engineers up at night for decades, what we call the tire paradox. I mean, think about it. For safety, you need a tire that really grips the road, especially when it's wet. That means high friction. But for fuel economy, you want the exact opposite. You want a tire that rolls as smoothly as possible, with very little resistance. So you've got these two goals, high friction and low energy loss, and they're completely at odds with each other. And this isn't just some small detail. The stakes are huge. For an average car, about 20%, a full fifth of the fuel you put in the tank, is used just to overcome the tire's rolling resistance. So solving this paradox isn't just a cool engineering problem. It's a massive deal for the environment and for our wallets. And the secret to solving it? Well, it lies at a scale you can't even see.
So let's zoom in, and I mean way in. The solution isn't on the outside, in the tire shape or tread pattern. No, you've got to go deep inside the material itself, into something called a polymer nanocomposite.
So, what's in the mix? Well, first up, you've got the polymer matrix. You can think of this as the rubbery foundation, just a tangled mess of long molecular chains from some specialized synthetic rubbers. Then, mixed into that rubber, you have nanoparticles. These are microscopic filler particles, things like carbon black or silica.
But, and this is the absolute key, you can't just toss these ingredients in a bowl and stir. The real magic, and the solution to that tire paradox, is all about how these tiny components are arranged. It's about building a precise architecture, but on a nanoscale.
So how do they arrange themselves? Well, it turns out the nanoparticles don't just drift around randomly in the rubber. They actually build their own structure. They self-assemble into what scientists call a filler network. It's like a hidden skeleton inside the material.
And this skeleton gets built in stages, from the bottom up. You start with the tiniest individual nanoparticles. These little guys clump together to form bigger pieces, which we call aggregates. Then, those aggregates link up, kind of like a chain. And finally, all those chains connect to form this huge, three-dimensional web that runs through the entire material, making it strong.
And look, this is not a small thing. The research is super clear on this. That filler network, that hidden skeleton, is the single most important factor. Basically, the strength and the shape of that network is what controls everything, from how the tire groups the road to how efficiently it rolls. So what holds this whole network together? The secret ingredient is something called the adsorbed polymer layer. It's just a really thin layer of the rubber's own polymer chains that gets stuck to the surface of the nanoparticles. You can think of it like molecular glue. It holds the aggregates together and makes the whole network stronger.
Okay, so this is where it gets really wild. And honestly, a little counterintuitive. To build this perfect nanoskeleton, you have to mix the ingredients. But it turns out that just mixing more and more can actually make the material weaker before it ever gets stronger. It's because there are two different things happening when you mix: distribution and dispersion. At first, with low energy, you're just distributing the clumps, spreading them out. But doing that actually breaks the fragile network chains that have already formed, so the material gets weaker. But if you crank up the energy, you get dispersion. Now you're not just moving the clumps, you're smashing them into smaller pieces. This creates way more surface area, which allows for tons of new, much stronger connections to form.
So the end result is pretty amazing. You mix with just a little bit of energy, and you're just breaking things apart. The material's viscosity drops, it gets weaker. But once you push past that point and put in enough energy to really disperse those particles, boom, the network rebuilds itself stronger than ever. Mastering this balancing act is exactly how engineers can fine-tune a tire for both amazing grip and incredible fuel efficiency.
And what's so cool is that this idea, this principle of designing a material's properties by controlling its internal nanoarchitecture, it goes way beyond tires. It's a cornerstone of modern material science, and it's popping up in fields you'd never expect, like medicine. Believe it or not, the exact same thinking is being used to save lives. In medicine, scientists are creating these advanced bioscaffolds, basically structures that help the body regrow tissue, by engineering their internal structure on a nanoscale to get just the right properties.
I mean, using this inside-out design, they're creating everything from smart wound dressings that help you heal faster to scaffolds that help the body regenerate bone and cartilage. They're even designing systems that deliver drugs right where they need to go and constructs for growing new blood vessels. It's amazing stuff.
Which brings us to the really big idea here.
We are entering this new era of designing materials from the inside out, literally building them nanoparticle by nanoparticle to have the exact properties that we need for the job.
So the bottom line is this. It doesn't matter if you're making a fuel-efficient tire or a life-saving medical implant. The principle is the same. By understanding and controlling that hidden, nanoscopic architecture, we can custom-build materials to solve pretty much any challenge we can dream up.
You know, we started with a simple paradox in a car tire. But the solution points to this incredible future. A future where we're no longer limited by the materials we happen to find. Instead, we're only limited by our imagination to design the materials we need. So that leaves just one question. If we can engineer things from the nanometer up, what impossible challenges will we solve next?